All right, for this exercise, we're going to just see what happens whenever you start mixing capacitors and op amps together. I think key to doing this is if you have a capacitor, let's say, oops, that's a bad color. Let's do a black capacitor. Let's say that's some value C, and we define the voltage across it as VC as a function of time, right? And let's say the current across through it will be IC as a function of time. Right? What is the relationship between that capacitor current and that capacitor voltage? Now remember, with resistors, it was very easy. It was just the voltage is proportional to the current times the resistance. Capacitors are, things that exist in time, right? Basically, they're saying the voltage isn't directly proportional to the current, but it's going to be directly proportional to the integral of the current. Similarly, we could say the current is going to be proportional to the derivative of the voltage across it. You can actually write this relationship out in two ways, and we're going to use it both ways. First of all, we can say the current through the capacitor as a function of time, of course, is what? C dV, C as a function of time, dt. So basically, the current through the capacitors is proportional to the capacitance itself and the derivative of the voltage across it with respect to time. All right? We can also say the voltage across the capacitor as a function of time is equal to 1 over C times the integral from 0 to t of the current through the capacitor of tau d tau. So I'm just using tau as sort of a stand-in variable here, but it's basically saying the voltage across the capacitors is proportional to 1 over C times the integral of the current through it over time, and the current through the capacitor is proportional to the capacitance times the derivative of the voltage across it. These are mutually supporting, just two different ways to write it. But we're going to use them, each one of these things, in two equations we're going to derive. In particular, we're going to look, first of all, at this circuit. So let me draw it out. I'm going to have an input voltage here, Vi of t. That's going to go into a capacitor. And that's going to go into an op amp, which we've not really mixed yet with capacitors. Let's call this R1. Let's call this C1. This output voltage I'm going to measure with respect to ground. Cool. Now let's make this to ground. So we have an input voltage with respect to ground, Vi. We have an output voltage, Vo. We have two components in an op amp. In negative feedback, this actually is very similar to a inverting op amp topology, which we've seen several times before already. So instead of having a capacitor here, we've already seen this exact circuit with a resistor here and a resistor here. Now, what's the capacitor going to do that's going to change it? At the high level, we can solve this exactly the same way. We're going to come up with an expression for the current flowing here. Let's call it I1. We're going to do KCL at this node and recognize that the current can't flow into the op amp, so whatever current I1 was here is actually going to be I1 here. We're also going to take advantage of the fact that since the op amp is in negative feedback, we're setting the voltage here at the non-inverting input, that means the inverting input is going to be the same voltage, which here is 0 volts, which is nice. And we're just going to solve it out like we've done. So for our expression for I1, as a function of time, because we're with capacitors now in the time domain, we need to generate our component equation. Now we can take this one up here and use it. Okay, we just need to map it over to the voltage which we're seeing here. The voltage across the capacitor in circuit-specific terms is going to be Vi minus 0 volts. Okay, so we could write more explicitly, if we wanted to, Vi equals Vc minus 0 volts. These are all functions of time. So we could say what? C1 d Vi of t minus 0 volts over dt. Now we know 0, the derivative of that with respect to time is 0. So really this is just saying C1 dVi as a function of time dt. We then can come up with a second equation for the output voltage, Vout, as a function of time will equal 0 volts minus I1 times R1. I1, R1. We know I1 now from here. So really this is saying what? V out as a function of time equals, let's merge these together, it'll be R1 and C1 joined together, a negative here, R1, C1, d VI, whoops, function of time, dt. Cool. Actually, let's do green. I feel like green. Now, we look at the circuit, what it's saying is the output voltage is based off of some, component values, but more importantly, the derivative of the input voltage. Very cool. Let's actually just make a note of that. It's taking the derivative, or the differentiating the input voltage derivative. Now I want to look at a second circuit right here. Same exact topology, we're just going to flip two components. So we're going to have an input voltage VI as a function of time. Now that's going to go through a resistor instead, R1, into the inverting input. This goes to ground. This is now a capacitor in the feedback position, not a resistor, C1. And I want to get this voltage out. I'm just going to move it up a little bit here so I have some writing room. So how would we solve this? Same deal as before. Let's figure out our I1. We'll recognize that I1 gets deflected up here, I2, because there's no current into the op-amp inputs. We also know, for example, that these two nodes are tied together because the op-amp's a negative feedback. Even if it's through a capacitor, there's still negative feedback here. All right, and this will become more and more apparent as we work with them more. So we know the voltage here and here are going to be tied together, or 0 in this case. So we can come up with a quick expression for I1. I1 equals VI as a function, and actually let me explicitly make these functions of time. I1 as a function of time equals VI of t minus 0. I'm not even going to bother writing that, over R1. We then know I1 and I2 right here are going to be the same thing, so we can come up with an expression for V out equals what? 0 volts minus whatever the voltage across that capacitor is. Now the voltage across the capacitor, we can go up here to our integral expression, and in particular that's going to be what? Minus 1 over C1 integral from 0 to t of I of, let's call it 2, but we know it's also 1, so I'm just going to say 1, of tau d tau. Now we have another expression for I1, which is in terms of the inputs and the hardwired components here, so we could rewrite this as V out as a function of time equals, get rid of the 0, there's going to be an over R1 we're going to pull out, so it'll be negative 1 over R1 C1 integral from 0 to t of Vi of tau d tau. Nice. Now looking at this equation, this is saying that the output voltage is based off of some constants again, right? And there's a negative, of course, but it's going to be based off of the integral of the input voltage. The previous one was based off of the derivative of the input voltage. And this is really cool, because what it's actually given us now are two circuits which we can complement other things which we've already developed and do mathematical operations on them. And this is actually revealing the primary reason why operational amplifiers are called operational amplifiers. Originally they were supposed to do mathematical operations, and we've already figured out with like the summing amplifier how to sum, right? Or with the difference amplifier how to subtract, or with the inverting or non-inverting amplifiers how to multiply by a constant. Well, these give us some calculus capabilities, right? We can take the derivative with this one right here and the integral with this one right here. And for those of you with maybe some control or robotics background, right, this is cool because now all of a sudden we have a derivative amplifier and we have an integral amplifier, and we do have a proportional amplifier, right? That would be maybe the inverting amplifier. If we remember, you know, let's say, I don't know, look like this, two resistors, right? R2, R1, VI, VO, right? And then it was saying what? VO equals negative R2 over R1 VI, right? So that's proportional, we could call that, right? Some just number proportional to the input. And together what you can actually do is come up with a PID controller, and PID, which stands for proportional integral derivative control. And so you've all of these three things together, you can turn them into a type of controller for, like, positioning or something like that, or robotics. And all it works about is, like, you have some signal that comes in, you split that signal three ways, one into your integrating amplifier, one into your derivative amplifier, and one into your proportional, and then add them back together, maybe with like a summing amplifier, and then use that for your control. Now, truth be told, in real life you don't use necessarily these amplifiers only like we've written right here. So for example, the derivative amplifier, the differentiator, is highly susceptible to noise. You could imagine if you had a voltage that came in here, right, and maybe just a real quick, like the plot of that voltage over time, even if you held it constant, if it was nice and flat, right, if we were to actually zoom in, you'd see little tiny up and down movements on the wire from just thermal noise or something, and that ends up, even though they're like very small in magnitude, right, that means they're changing very quickly, and they can be actually greatly amplified in a circuit like this. Similarly, an integrator can be tricky to work with because, like, anytime you integrate, like, you kind of need a starting point, right? Are you integrating since the beginning of time or something? Or what is t equals 0? So you need to add in supporting circuitry and stuff to handle that. But originally, historically, PID controllers were implemented in circuits using, this for your D, this for your I, and something like this for your proportional. And you can actually, people made them work, Nowadays, a lot of this is done digitally, because you can do a lot of stuff with that. But this is how you can actually do it with circuits, and there are still times and places where a analog implementation of that has a need.